Hello, welcome, sir. Good afternoon. Uh, Desmond, sir, can you hear me?
I can hear you.
Okay, okay.
Yes.
Yes, it is visible. Your PPT is visible.
Yes.
I can see.
Can you see my page now, my screen?
Yes, I can see recent published works.
Yes, yes, great. So I'll go to the first page. I'll go to the first page there.
Yeah, recent developments in 5G.
Yes.
It's visible. Sainaj madam will join in 5 minutes.
Okay then.
Okay.
Can you see the full screen or partial of the screen?
It's showing partial screen, not full.
Not the full screen. What about this? I was seeing the partial screen or the full screen. Because I've got two screens.
I'm showing two screens.
Sorry? Two screens.
Two screens.
So I have to switch to the one on my right. So I'm going to check. So how am I supposed to?
Good afternoon, Dr. Sim.
Yes.
Yeah, Shahnaz here.
Yes,
Good afternoon.
I'm having a problem now trying to switch the screen. Let me see how I'm supposed to switch the screen now. I'm not quite used to.
Sir, you can press F5 and then it will come.
Press again. What? Press F5. Because I'm showing only the partial screen, isn't it? Yes.
Yes. Now you can minimize the right side window.
Minimize the right side window. No, that minimize the right side because I believe there's a way to switch my screen.
No problem, sir. You can just make full screen. Make this full screen. Yes, from here only. From that side, bottom. Yes. Now it's okay. You can.
Still, I would like to switch to the next screen.
Then arrow. You can press arrow key. Down arrow.
Down arrow.
Of keyboard.
Keyword. No, I don't quite understand it. I would like to switch out again and come back in.
Okay.
Now let me see if I can switch the screen. No, supposed to do this. Okay. Strange. I couldn't find it. Still, it comes back to here.
And this is also okay. This is okay. Visible. Everything is visible. Just two screens. We say one is small and one bigger one.
Yes. I know that I'm trying to switch my screen. How am I supposed to do that? Yes, this one. It's strange. I think I just have to bear with this. Can you see that I'm switching the pages now?
Okay, yes, switching. Yes.
Okay then. So we will start in 5 minutes.
Yes, sir.
Okay then.喂，对，我现在开会没办法。好。
Is it okay now, Professor Sim?
I'm okay, but still can't switch my screen. But I just have to bear with the left one.
Yeah.
The one that you're seeing at the moment.
Yeah.
Okay. So how is everything in your university?
Yeah, it's fine, sir. It's fine here. We are staying in campus itself, so we don't have any problem. Like whenever it is required, ours is like a residential institute. We have residential campus.
Yes.
So,
will
and
the
we are
student
taking
be
online classes. Students
Yeah.
are not allowed. Students are not coming into the institutes.
Right.
Going through online mode.
At the moment, right now, our situation is much better.
Sir, you are not audible, sir. I think you are unmuted.
You can't hear me?
You have to unmute. You are muted, sir.
Is it?
Sir, you are not audible, sir.
No? Can you hear me?
Sim, sir, you are not audible.
Is it? I thought my sound. Can you hear me?
Dr. Sim?
Yes,
Sim, you are
can
not,
you hear me?
Yeah, you are not. Yeah, now we can hear you.
You can hear me now?
Yeah.
Okay then, great. Yeah, so you have to inform me if you can't hear me. Things are okay in my site on my site now. Students will be returning on Monday next week.
What is the situation of COVID? Is it now normalized?
Yes, it's contained right now in Taiwan.
Okay. Yeah.
So students are coming back. Overseas students will be back in late October.
Great, sir.
Yes.
So how much is the strength, sir, in your department of students?
In my department?
Yeah.
Number of students about 746.
Oh my God,
undergraduate.
in electrical stream?
Yes.
Oh,
yes. About 746. We've got about around about 39 postgraduate, and we have got 18 faculties member, including me. So we are quite a large department.
Yes. Yeah. Great, sir.
And
good to connect you, sir. Thank you very much.
Sure.
Accepted our invitation. Sir, shall we do one thing? Shall we put the screen off? I will introduce you and then we'll start the presentation.
Sure. Yeah. Sure.
We'll just wait for 2-3 minutes because participants are still joining. It is not 3 p.m.
Sure, no problem.
So I had this in my mind that after your presentation, as soon as the director sir will join 10 minutes before finishing your presentation. So we'll immediately start the valedictory and I will listen to your address and then maybe we can...
You hear me? Yeah, I can hear you.
Yeah. Yes, sir. Yes. So you were on leave, sir? 4 days you were on leave?
Yes. I have to go to Taipei.
Okay.
Yeah, I got a meeting, and yesterday I had a 5G workshop in Taipei.
Okay.
Yeah, the topic is on AIP, antenna in package.
Okay.
Yeah, but today's my topic will be on sub 6 gigahertz antenna, but not on millimeter wave. Yeah,
okay.
they are more interested in millimeter wave in Taiwan right now. Yes.
Sir, another time get some time so that we can have those lectures also from you.
If I can find time for that.
Because now it has become so like, though there are disadvantages of COVID-19, there are many advantages also. At least we could, if we could get connected.
Yes, true about that.
Yeah. Many senior faculty members have joined this faculty development program, sir. Scientists from ISRO, Professor Mahadevan is also there. Professor Raghavan from NIT Trichy is also there. So many senior faculty members and legends of this particular fields, they have joined this particular FDP.
Sure.
And we have international participants also.
Sure, thank you. It is nice to have this faculty development program.
Yes,
we never had that.
Oh. You conduct, sir, you organize one such, we will join. It would be our pleasure to.
Yeah, recently I'm quite busy. Yeah, I have to keep running around the whole island.
Hello,
because they have been a lot of topics, especially industrial requirement.
Hello, sir.
Can you hear me?
No? Can you hear me?
Yes, I can hear you,
yes,
but yes, I can hear you.
I'm actually Dr. Raghavan. Once I was invited by Taipei conference.
Yes.
It was a medical informatics conference. So I was there for 5 days.
Yes.
That's near to your place, isn't it?
Sorry, can you speak louder? Taipei, yes, I know that. Yeah. So you'll be in Taipei.
They invited me for a small medical informatics conference.
So when
sir, he is Professor Raghavan from NIT Trichy, legend in microwave engineering.
So you will be in Taipei for 5 days.
Yeah.
So
2 years before.
2 years before.
Yeah.
Okay then. But at the moment right now we can't do any traveling.
Okay.
Yeah, all the travel has been banned. So I have to stay in the university.
So you know Ito, isn't it? Ito? Tatsu Ito?
Ito?
Computational electromagnetics and all.
You mean Professor Ito from Japan?
Caltech.
Oh, Caltech. No.
Okay.
No, I didn't know him.
Kevu, Bozi.
Kewu, yes. Kewu. I've seen him a couple of times. He came to Taipei a couple of years ago for the wireless power transfer conference.
We are doing his work. Substrate integrated waveguide, SAW.
Yes, SSW. Yes.
Okay, sir. Very happy to meet you. Okay.
Yes. Thank you. Kewu is a pioneer in SIW. We have done some SIW as well. I can show it to you later on. Because at the moment right now, we have to build a 5G 5G millimeter wave cell base station for the industry. So we have to use the SIW for the feeding network.
So, sir, 25 participants have joined yet, and they are joining still. We'll wait for 2 minutes and then we'll start.
Sure.
Professor Mahadevan, he's a scientist from ISRO. He has also joined. Good afternoon, sir. Good afternoon, Raghavan sir. Good afternoon, Mahadevan sir.
Good afternoon. And it's a pleasure for us to meet Dr. Desmond Sim in this such an important topic. See, wherever there is a 5G topic, there will be a lot of students who will be interested in that because it is the order of the day.
Thank you.
And then we find that, of course, specifically in Taiwan, others that miniaturized components are really very good. Specifically, I've seen some microwave components like circulators, isolators,
Yes.
etc., coming out in such fantastic size, you cannot beat. And they were very used. And then semiconductor industries have really come up very well in that area. So it's a very great advancement. Is this thing? I'm sure they must have been all be supported by universities research. So
Yes.
the industries have come up very well.
Yes, we do have some support from the industry, but it's very unfortunate that I cannot show it to all of you.
Yeah, that's fine. But
Yes.
no, industries are also very much benefited by the research in the institutes, in the universities.
Yes.
That's why we have physically seen some excellent components, specifically some of these isolated circulators in the microwave area. They were available for as low as $90 to $100, and such small miniaturized ones from Taiwan.
Yes.
So it was extremely useful for doing the breadboarding of the whole system, because for breadboarding you don't buy a space qualified component; it will be very expensive. So initially, and then afterwards, when you order for qualified version.
Yes.
So that is how we do it. So I remember very much so wish you all the very best in the advancement in the industry and university.
Yes, thank you.
Shall we start, sir, now?
Yes, we sure we can start now.
Yeah,
I'm going to share my screen now.
Just wait, sir. I will introduce you and then we'll start.
Oh, sure.
Yeah. A warm afternoon to all present here. The galaxy of intellectuals, invited guests, renowned academicians, and dear research scholars. I, Shahnaz Ayub, your host today on behalf of Department of Electronics and Communication Engineering, BIET Jhansi, and on my own behalf, I welcome you all to session 2 of 5th day of FDP on electromagnetics to 5G, jointly organized by BIET Jhansi, SPIU, UP, IST, and Numergion. It is rightly said, science, engineering, technology, no country, because knowledge belongs to humanity and is the torch which illuminates the world. Yes, we have among us Professor Chow and Desmond Sim. He born in Singapore in 1971. He received the BSc degree from Engineering Department, University of Leicester, UK in 1998, and the PhD degree from the Radio System Group Engineering Department, University of Leicester in 2003. From 2003 to 2007, he was an assistant professor with the Department of Computer and Communication Engineering, Tsinghua Technology University, Changhua, Taiwan. In 2007, he joined the Department of Electrical Engineering, Fengxia University, Taichung, Taiwan, as an associate professor, where he became a full professor in 2012 and as a distinguished professor in 2017. He has served as the Executive Officer of Master's Program with the College of Information and Electrical Engineering, Industrial Research and Development, the Director of Intelligent IoT Industrial PhD Program between August 2015 to July 2018. He has served as the director of the Antennas and Microwave Circuits Innovation Research Center in Fengxia University between 2016 to 2019. He is now serving as the head of the Department of Electrical Engineering in Fengxia University, Taiwan. He has authored and co-authored over 160 SCI papers. His current research interests include antenna design, VHF, UHF, tropospheric propagation, and RFID applications. He is a fellow of the Institute of Engineering and Technology, FIET, a senior member of the IEEE Antennas and Propagation Society, and a life member of the IAET. He has served as a chapter chair of the IEEE AP Society Taipei chapter from Jan 2016 to December 2017. And he is the founding chapter chair of the IEEE Council of RFID Taipei chapter from October 2017. He is now serving as the Associate Editor of IEEE, AWPL, IEEE Access, IEEE Journal of RFID, and International Journal of RF and Microwave Computer Aided Engineering. Since October 2016, he has been serving as the technical consultant of SAG Group, one of the largest RFID tag manufacturers in Taiwan. He also is the consultant of Avery, the largest PCB manufacturer in mainland China since August 2018. He was the recipient of the IEEE Antennas and Propagation Society Outstanding Reviewer Award, IEEE Transaction Antennas and Propagation for 7 consecutive years between 2014 to 2020. He has also received the Outstanding Associate Editor Award from the IEEE Antennas Wireless and Propagation Letters in July 2018. We have among us such a legend. Professor Sim will deliver talk on recent developments in 5G sub-6 GHz antenna designs for smartphone applications. Over to you, sir.
Thank you very much. I have to share my screen right now. I think I'll share my screen too. Let me check here. Now, can you see my screen?
Yes, sir.
Yes, right. So thank you for spending so much time for introducing me. And thank you for inviting me over. I can see there are 39 people online right now. So 5G has been a hot topic for the last couple of years. And I entered this domain about 5 years ago. Leading by one of the well-known professor known as King Lu Wong. Now, if you are in the antenna design area, you will know his name. But anyway, today's my topic is the recent development in sub-6. And I also lastly, I will introduce some of the works that we have done in Fengjia University. Because so first of all, I'd like to introduce my university. We are actually an island. If you have been to Taiwan, I believe one of the professors has been to Taipei. So Taipei is at the top. Wait a minute, give me a minute. Yes, at the top side out here. And pointer laser, yes, that's right. And we're actually in the middle down here, known as Taichung. And if you look at the picture in the middle down here, this is the front door of our university. And we do not have any cafeteria in the university, because right outside the door, you can see it's a huge night market in there. And we have the largest night market in Taiwan. So all the eating and catering will be right outside the front door. So I'm not going to talk about the history of our university, because I think I could be spending a lot of time explaining what's 5G. I reckon that most of you may not be in the field of our antenna. So I'm not going to introduce a lot about the antenna design, but the process of how we can attain 5G technology. Now, first of all, if you look at 5G technology, you have to realize that we have to first embrace the 4.5G, and that is the LTE Advanced Pro. At the moment right now, we're still running LTE Advanced Pro. It is only in June this year that the 5G is actually being implemented, but that were only on sub-6 GHz and not in millimeter wave. And later on, I'll explain what is sub-6 GHz and what is millimeter wave for 5G. And let's look at the evolution right now for mobile phone. Now, if you're as old as me, almost about 50 years old, then you'll be able to reckon all the changes, because in the 1980s, we got the really huge Motorola phone. It's quite heavy. And slowly, when Nokia came up with the first well-known small phone 3310, then slowly we got our first UK mobile phone, and we go into 2G, where we got GSM, and then we moved to 3G, and last but not least, right now, 10 years ago, we're beginning to have a smartphone known as the 4G phone. But slowly, when we move into 5G, things are beginning to be a little bit different at the moment. Because at the moment right now, if you look at the trend in the mobile phone, I should put another pictures in here. We are now, the recent phone right now is the foldable type. It's a foldable type, where you have to use a flexible substrate. And this is something that we are looking into right now. So what I'm going to advise you right now, if I really go into 5G, then you have to be friend with those people who are doing chemistry. So at the moment right now in my department, we are going to employ 1 or 2 professors who are in chemistry, because they are the one that will be able to join my group and try to provide some advancement in, especially in all the dielectric substrate that we can use. So let's look at the 3GPP right now. Now, why is 3GPP is the 3rd generation partnership group. Now, this group will try to say that what kind of mobile technology that we'll be using. And so if you look at LTE right now, we began from release 8 and release 10, 12, 13, and now we are slowly moving to release 12. And if you look at the bandwidth and the downlink and the uplink, you can see that initially they are quite small. So these are all for 4G, but then slowly right now we are moving to the LTE Advanced Pro. I believe now we are using that, and that will be 3GPP release 13 and 14. So what is 4.5G at the moment right now? Now, remember for 4.5G, at this time, we are using carrier aggregation, 3D full dimension MIMO. I'll explain that later on, and especially single cell point to multi-point. But this will change as 5G arrives, because we are using what we so-called a MIMO technology that I will introduce later on. So the release 15 for 3GPP, let me look at my pointer right now. Yes. It has been detailed in June 2016 and has been completed. And so now we are moving to release 16. But at the moment, right, we are stuck in release 16 and not moving forward because of COVID-19. So especially for single cell point to multi-point cell, so how do we going to achieve that? And one thing that we can do right now is to use what you so-called a full dimensional MIMO type. And what is exactly full dimensional MIMO? The answer to that is that you need to have a conventional multi-antenna system where the beam of the cell will go up and down and from sideways as well. So if you look at the picture down here, you can see that this is what we so-called a full dimension MIMO in here. So besides going left and right, it can go up and down. So that our future, which means that in the future, we are going to have hundreds of thousands of such kind of antenna beside us in the building, outside the building, where you can see that besides you having an elevational beamforming, as well, we will have an azimuth beamforming. And so this is one of the antenna design that has been built, I believe, in Europe, and they have been tested. You can see that in the future right now, we will be seeing more and more of this type of base station. But this is kind of base station is really difficult to build, because you have to build like at least 64 antenna array element, and in some country they have already built up to 1024, means 1024 array element. And the greatest challenge for that is the feeding network itself, because if you are not careful about it in the feeding network, you will incur a lot of losses. And the next issue is the heat, because what happens is that the power that is going to be input into this kind of a base station will be about 6 to 7 times larger than our 4G cell, meaning that you need to have a large heat sink to dissipate all the heat. But at the moment right now, because you are given such a small volume size, so there's a problem that we are facing at the moment, is that we can't dissipate the heat. And so someone came up with the idea and say that we need to use different kind of substrate, a substrate that can direct the heat away from the antenna. And that's the reason why in the beginning I say that from now on, if you try to work in 5G, then you have to be friends with people doing chemistry, so that they can help you to develop a new kind of substrate that can dissipate the heat very easily. And so, as I said before, right now there are lots of people that are using what you so-called massive MIMO antenna design in the near future for the base station. But the question right now is, what about the smartphone design? Because what happened is that we are facing a great challenge in smartphone antennas design, because the smartphone itself is small. It's very small in volume. The thickness itself cannot be more than a centimeter. And the moment right now is around about 7 to 8 millimeter. So with such a low profile type of a smartphone, then if you take away the thickness of the screen, which is around about 1 millimeter, then you are left with about 6 to 7 millimeter of thickness. And you have to consider your battery and etc. So I'm going to show you with some of the pictures afterwards. So I'm going to skip this on the introduction from 1G to 5G. So let's talk about 5G right now. Some people, they don't understand what's 5G, and they keep asking me what's so good about 5G. And there's a lot of talking about 5G, but most people do not really understand what is 5G. And it is quite easily understandable because it has got 3 criteria. Now, there are 3 criteria in 5G, and one of them is this. The throughput must be over 10 gigabits per second. And at the moment right now, they're talking about 25 gigabits per second. But Amazon has tried their 5G network, and the most they can go up to is right now is about 3 gigabits. So the initial criteria was not met. It's not met at the moment. It's not. No one has ever gone up to about 10 gigabits at the moment. And the next consideration is 1 millisecond latency, meaning that the delay must be no more than a millisecond. And this is very important for 5G, especially if you need to implement that into a driverless car. So the reaction of this signal transmission must be so fast enough that it will not hit another car. And next is the connection per kilometer square must be 1 million, meaning that if I'm using this 5G system, and this mobile phone can connect up to about 1 million devices within a kilometer square area. So you can see that these 3 criteria right now is holding us to try to develop 5G technology. And I'll talk about it, I'll elaborate that later on. And first, let's look at the speed or the data throughput and the comparison between 3G and 5G. As you can see right now, in 3G, during the time when we have 3G, if you need to download a 2-hour long Guardians of the Galaxy, you need to spend 26 hours. But if it goes to 5G, if you have the 10 gigabits per second, then you only need about 3.6 seconds to download that. And if you compare to 4G, you need about 6 minutes. So this is the magic of 5G. Your download and your uploading will be so fast, it's in the blink of the eye. And it's a good news, but it's also a bad news. And the reason for the good news is that we can enjoy all the data streaming so fast and even don't have the time for a coffee. But then the bad news is that it's the security. And that's why in our school right now, there's a group of people has tried to develop some kind of data coding, and that is for the security of the nation. And this is the reason why Donald Trump in America is trying to hold the neck of China and trying to prevent them from further development in 5G. And that is because of data security. Imagine the data is so fast. You can download a 20 gigabytes file in like 2 seconds. It's a huge problem right now in security. If the Chinese break into your security server, he only needs a few seconds to download almost everything. And that's why the security, data security, will be the next thing for 5G. So how do we can achieve that to have such a 10 gigabits per second? Because when we first talked to those people in communication, they told us that there's no way for hardware can do that, especially for mobile phone. Because in their mind, because they don't really understand mobile phone, and they keep saying that, no, there's no way that you can do that. But we keep telling them, if we can use massive MIMO, it's the only one key technology that we can do that for hardware. So let's look at for why we can do that. Now, if you look at this screen right now, if we are using sub-6 gigahertz, what we are doing right now is we call so-called a a multi-stream type. For multi-stream type, meaning that you have a base station, and this base station will be uploading and downloading data from all the phone below it. But if you are using millimeter wave right now, especially those above 6 gigahertz, we are using what you so-called a narrow beamforming. A narrow beamforming meaning that the beam itself will start switching left and right and up and down, as I've shown you, a full dimensional type. So what is a massive MIMO system? Meaning that it has a large scale of antenna system, in which that the antenna is the base station itself can has an antenna elements up to about 256. And I'm sorry about that, for the phone. And you can see that if you are using this kind of technology, you'll be able to connect to tablet, PC, and also smartphone. At the moment right now, we're talking about isolated antennas for smartphone. You can only go up to about 16 of them. So let's look at the spectrum right now. So at the moment for the spectrum, I should have changed this because it has been renewed. But at least for those above 6 gigahertz right now, the Americans are trying to take over 28 and 39. And there's some talking about 40 and also 66 gigahertz at that point. And then the fastest country that we can see right now is the Japanese, the European, and the Korean, and the American, and also they're from China. And so they're trying to allocate the frequency bands to their interests. I'm not so sure about India right now, but in Taiwan, we haven't really come into a conclusion that what kind of millimeter wave band that we should be using. And our best guess is that we are going to use it for the same as what the American is using at the moment. And so how can we develop that? Now, for those people who are working in millimeter wave, they keep thinking that 5G is equivalent to millimeter wave. To some people, they keep saying that. But to us, we do not think so. 5G does not equivalent to millimeter wave. Yes, we will approach millimeter wave this year and the next year and the next 10 years, but it is not now. And is there no alternative? Now remember that if you're trying to buy the VNA, it'd be hundreds of thousands of US dollars. But if for those that are working in 38 gigahertz, and if the frequency band goes so high, then the prices of all these elements will be very high as well. So it is very difficult for researchers to do their work because things are so expensive. So we were thinking at that time right now, 2 years ago, is there no alternative? We can use 5G technology, but first of all, we try to avoid millimeter wave. And indeed, in 2015, the WRC came up with an allocation of a spectrum at that time. And it does help us in trying to develop a lower band, such as a C band, as you can see from here, between 3004 to 3006 megahertz. They try to allocate this band for us, and that's back in 2015. And so they say that, well, we can use this band for 5G. So we are quite happy about that. And so after 2015, you can see there are lots of antenna design coming out from smartphone. So our conclusion for this is that 5G is not necessarily equivalent to millimeter wave. And I'll answer to that question with more data. I'm going to switch to this page. And this is the allocation at the moment right now for all the 5G spectrum around the world. As you can see right now, they have been allocated that and break the spectrum into what is so-called N77, N78, N79. I will explain that later. And you can see that some of the countries are using quite a bizarre spectrum, especially the Japanese and the Chinese. You can see that they're using 4.4 to 5 gigahertz. And so they name it as N79 band. And if you can see down here right now, the European and also the American, they were thinking of using a 60 gigahertz band in here. So maybe in the near future, we'll be seeing a 5G millimeter wave switch to about 66 gigahertz. And that could be a trend in the next 5 years. So I'm going to skip this and goes to this. So at the moment right now, I believe 2 years ago, they came up with what you so-called FR1 and FR2 because most people, they couldn't really understand the frequency spectrum of 5G. So they say that, well, for those below 6 gigahertz or below between 400 and I believe there's a change in frequency right now, between 450 to 6,000 megahertz, and you'll be named as frequency range 1, known as FR1. And if you are above that, from 24 gigahertz to about 100 gigahertz, then you are named as the frequency range 2. So if someone told you that I'm working on FR2, you'll know that he's working on millimeter wave 5G. And if he's working on FR1, then he'll be working in the sub 6 gigahertz of 5G. So at the moment, as I said before, right now, they have broke the 5G sub 6 gigahertz into 3 types of band. And one of the band is known as N77, between 3.3 to 4.2, N78 between 3.3 to 3.8, and N79, and that is 4.4 to 5 gigahertz. And I look at the one on the right side right now. This is I believe a picture from Qualcomm, and Qualcomm at the moment right now has developed a new Snapdragon known as the X60. The X60 itself right now, for this new Qualcomm modem chip, you'll be able to use the AIP known as QTM525, and also at the same time right now, it can control the sub 6 gigahertz band. And this chip will be released next year in 2021. And so now, recently there has been a change in frequency range 1. And if you look at the red color at the bottom down here, you can see that there has been a change. Initially, it was up to about 6,000 megahertz, and then they changed it to 7125. This change was changed, I think, somewhere back in this year, in April or May. There's a change in here. And why there's a change in here? And that is because of Wi-Fi 6E. Now, if you go into the internet and search for Wi-Fi 6E extended, you'll be able to see that they are now using about 5 gigahertz all the way to 7,125. And because of this change in frequency right now, up to about 7 gigahertz, and lots of chamber has to change. Because at the moment right now, most of the chamber can only measure the antenna up to about 6 gigahertz. And because of this newly released band known as the Wi-Fi 6 extended, and of this FR1 that goes all the way up to 7.125 megahertz. So right now, everyone is trying to change, especially the Broadcom has already developed the Wi-Fi 6E chip. And so let's look at this page right now. And this page will explain to us. I can only hold the old data, but you can also see that from here. Now let's look at this table in here, the channel capacity, and I'll explain to you why we can achieve up to 10 gigabits per second. Because as I said before right now, previously those people who were in communication, they would say that there's no way that we can develop a mobile phone and mobile device that can receive up to 10 gigabits per second. And we tell them that we can do that. So Professor King Lu Wong in Taiwan, he developed this table and tried to show it to them. Now, if you look very carefully right now, this is N in here is the number of received antenna, and M in here is the number of base station antenna. So this received antenna is the mobile phone antenna, and the one on here, M1248, is the base station antenna. I repeat that. So let's look at how we can see that. So if you try to simulate the channel capacity, now if you have got one antenna in my antenna, if I have one antenna in my mobile phone, and my base station has got one antenna, then the most we can get is up to about 6 bits per second per hertz, and that's it. But if you slowly increase the number of antenna in your mobile phone without changing the number of antennas in your base station, let's say your base station still maintained as 1, the most you can get is about 9.5 bits per second per hertz, and that's not much. But you know that the smartphone, it has a limited volume. So the most we can have right now is put 8 5G antenna into there. And that's the maximum at the moment we can go. So the idea is that it can increase the number of antenna in the base station. So if you look at this chart in here right now, if I have got 8 antennas, sub 6 gigahertz antenna in my mobile phone, and I slowly increase the number of antenna in my base station, you can see that this is 1 and this is 8, the orange color, meaning that I jump from 9.5 all the way up to about 44 bits per second per hertz. And what does it mean in this case? 43.97, let's say it's about 44, meaning that it is 44 bits per second per hertz. What about if I multiply that by 200 megahertz? Meaning that if I got a bandwidth of 200 megahertz for my sub 6 gigahertz band, meaning that if I multiply this number with 200 megahertz, then I will get about 8.8 gigabits per second. So from this data, it is telling us a story that indeed we can do that. And after Professor Wong has developed this chart, he in one of the conferences back in 2017, he provided a MIMO demo for us. And this is an 8x12 MIMO system developed by Professor Wong. And in here, you can see that he showed us that he can develop up to about a 5.04 or 5 gigabits per second throughput. And this is real because we have sent someone up there and try to touch the phone, and the throughput reduces. So this is the mobile phone we're talking about. And here is a prototype base station. And on this stage, it's showing us that indeed we can do that. And so, and here's also some of the pictures that we have joined that conferences. So what in this picture on the right down here, Professor Wong is asking his student to use his left hand to touch the phone, the mobile phone in here, to touch it. So if you had a hands effect that's holding this phone, then obviously the throughput will be reduced from 5 to 3.2 gigabits per second. So during his experiment in here, showing us during one of the conference conducted in Taiwan, then he has proof that indeed in 5G technology, even if we do not use millimeter wave, we can still provide up to 3 gigabits per second. So let's look at some of the antenna design. I know that most of you are not in antenna design, so I'll go a little bit faster in this case. Back in 2015, as I said before, right, the WRC has released that you can use 3,400 to 3,600. And so after that, lots of antenna design has been shown to us that they can develop this kind of technology by using all kinds of loop antenna or monopole antenna. So this is one of the earliest antenna that we have developed together with my friend in China. This is a monopole antenna that together integrate with the 4G antenna on top of here. So the green color and red color antenna down here at the bottom edge is the 4G antenna. And those alongside down here, the green color tab is our monopole antenna, which are for the sub 6 gigahertz. And you can see in here at the bottom corner in here, so the 4G antenna can cover all the GSM band, the UMTS, and the LTE band. And our sub 6 gigahertz antenna, or 5G antenna, can cover between 3.4 to 3.6 gigahertz. So I'm not going to go into the inside of how we can we design that. And if you're interested, you can look into this paper. So this is another antenna that we have developed back in 2016, and it's published in IEEE transaction. at that time, we were talking about a high isolation type, especially for the radiation. So we came up with the idea is that the monopole antenna that we've developed, the blue color type in here, will have an X-orientated radiation pattern, and while the slot antenna in here will have a Y-orientation radiation pattern. So these two antennas will not affect each other, as you can see in here. So you can see that the Y-shaped slot antenna will have a Y-axis direction, and the other one will have an X-axis direction. So that if you look into this picture right now, you can see that the radiation pattern are pointing away from each other. So this is very important for 5G antenna. Your radiation pattern must be pointing away from each other. And because of that, you can have a larger isolation between each antenna port, and then you can get a much better ECC. So I'm going to skip this. Next, at that time, we have to talk about the Jhansi effect. So because we are lacking in funding to find a real phantom hand, we have to use a kind of a simulation software known as SAMCAT or the NSOFT HFSS. So I believe that this is using SAMCAT. So you have a dual hand, using two hands to hold the phone. So by using these two hands to hold the phone, you can see that even if I'm using two hands to hold the phone, the most I'm blocking right now is antenna 1, antenna 2, 3, and 4. So we are blocking the slot antenna. But even if I hold it this way, trying to play a game, I still have antenna 6, 7, 4, 5, and 8, and they are still free, meaning that our hands are not touching it. And so that you can see from here that if the hand is very close to the antenna 1 and 2, then the efficiency would drop from about 40 all the way down to 20. And antenna 5 and 6 still maintain about 40% of efficiency. And this is the requirement from the industry. And next you can see that this is a single hand mode type. And besides using a dual hand, you need to use a single hand type. So in here, we also try to simulate using a single hand. As you can see that the antenna in here on the top left corner and left and right top corner in here, and also the antenna below it, they are not affected by the Jhansi effect. So you can see from the efficiency simulation in here right now, these four antenna 1, antenna 2, and especially antenna 7 and 8, they are all affected, but the other four are not affected at all. So Professor King Lu Wong came up with the idea and say that back in about 4 years ago, he says that why not we have antennas that are only built on the upper section of the phone, and because we have to hold the phone, right, single hand, with the hold the phone as you can see in here. So we are holding the phone, meaning that the lower section, the antenna located at the lower section down here will be mostly affected. The EM will be mostly affected. So if that is the case, we just have to push all the antenna all the way to the upper section. Now the problem with that, putting all the antenna into upper section, meaning that your antenna got to be smaller. And because you're only using the upper section, meaning that all the antenna has been pushed to that way in such a way that they will be very, very close to each other. And if you are learning EM, you know that if two radiators are placing very close together, they will have a coupling effect. So coupling effect is no good for antenna. So let's look at how Professor Wong can do that. So Professor, if you look at the picture in the middle down here, you can see that Professor Wong has tried to avoid the Jhansi effect by pushing all the 8 antennas all the way to the top section. And the antenna design is this kind of design. And in order to reduce the coupling, he has used a kind of technology called the neutralization line. But down here, I'm not going to introduce that in detail. But as you can see that this is the way that he has tried to explain to us at that time, back 4 years ago, saying that we should put our antenna in the top section. But obviously, we cannot do that at the moment because we just can't give up our 4G antenna, our NFC antenna, and there are still other antennas that we need to take care of. So the industry rejected this idea of putting all the antennas to the top section. But anyway, this is a very good paper. If you are interested, please read that. So I'm going to skip some of the data, but look at page 37. Now, so Professor Wong, as I said before, right now he says that we're going to put all the antennas on top. Now the reason is that you can see it from here. Now we put 4 antennas to the left and 4 antennas to the right. So if you're trying to calculate the throughput with 16 QAM and only about 1.4 megahertz bandwidth, you can get approximately about 11.41 megabits per second. And if you use your hand to slowly touch it, you'll be able to see that even though you have these 2 fingers, the thumb and this finger, index finger is touching the point A and B, but still you can still maintain your throughput up to about 11. This is at the distance of 6 meters between the receiver and the transmitter. And if you look at these results, you'll be able to understand why Professor Wong from Taiwan, and he's trying to tell us that we need to put the antennas into the top section. So he came up with another design back 3 years ago. And he also came up with what you so-called a building block design. Now, his previous design, you can see that it has got 8 ports in here, and each port has got 1 antenna. But then in 3 years ago, he came up with a really nice design, using a technology known as the building block, meaning that I'm going to have my ground at the middle of the frame, and then I'm going to put 2 antennas very close to each other, And if I am not wrong, I think the length is about 10 millimeter. It's 10 millimeter by about 7. Very, very small antenna. And you got 2 antennas together, one on top of each other, as you can see from here. Right, this one antenna, this another one. So he gave it a name known as the building block. So at the moment right now, a lot of people from a lot of scholars in China, they are trying to use this kind of technology at the moment, trying to squeeze the size of the antenna so compact they can be placed together. But the problem with this kind of building block design is that the coupling between the antenna will be very large. So Professor Wong came up with the idea of using what you so-called a coupling technology, meaning that if you look at the design here, if I try to excite port 1, then in point A, then the energy will be coupled up to this main radiator, go all the way down to point C, and go all the way to point D, and from point D, he tried to short it to the ground. So if that is the case right now, if I try to short it to the ground, then there will be no energy that will be coupled to point in this strip in point E. And so we can see that if I try to excite the top antenna, and you can see there's a blue color down here in the bottom antenna, meaning that there'll be very less coupling between antenna 1 and antenna 2, and vice versa also for port 2 excitation. And so the idea of using this copper fit, because of him, has been developed right now by many researchers, and I can show you afterwards some of the design that we have done. So this is also one of the measurement he has done by using a real hand and trying to cover all the antennas. So I'm going to skip this and move to other kind of, let me see if there's anything interesting. I'm going to show you this. At the moment right now in the open literature, the maximum number of 5G sub-6 gigahertz that we can use is up to about 16 of them. As you can see here, right, Professor King Lu Wong came up with the idea of using 16. And instead of using this building block method, he's trying to place them on the same plane, but then each antenna must be very, very close to each other. And the problem with having such very closely displaced antenna together is that he has got a mismatch, especially in the higher band in here. And so the 6 dB return loss, or the S11, is not that good. And this is the price for him to pay for trying to put all the antenna very closely together. And obviously, because he has to put two antennas very close to each other, then he has to use, as again, as I said before, he's using what you so-called a neutralization line to decouple the two antenna. And for each set of antenna between antenna 1, 2, and 3, 4, he also used a neutralization line that, in this case right now, he has to use an inductor trying to reduce the coupling effects between these two sets of antenna. So we'll skip some of the results and go into some of the design consideration at the moment. So now, if you're considering a bandwidth, for example, 100 megahertz. So if I'm using an 8x8 MIMO, meaning that I have 8 antennas in my mobile phone in sub-6, and I got another 8 antennas in my base station antenna. So base station has got 8 antenna, and mobile phone has got 8 antenna, so it's known as 8x8. And so if I'm using an 8x8 MIMO, then, and also at the same time, we have a high QAM with about 256, and our throughput can be expected to be 3.7. So we are going to increase the bandwidth to 200, as I said before. Then the 8x8 MIMO throughput for 256 QAM will be up to 7.4 gigabits. So this answers to some of the questions that has been raised by the communication people that keep telling us that we are not going to make it. But indeed, we have made it in such a way that now at the moment, we can go up to about 5 and 7. So I believe the largest, the highest throughput right now in Taiwan that we have developed is about 7 gigabits per second. So very soon that we will go up to 10 gigabits, meaning that, if you still remember, this is the first criteria for 5G technology. Remember, there are 3 criteria: 10 gigabits throughput, 1 millisecond latency, 1 million connection per kilometer square. So indeed, we can use a massive MIMO mobile device plus a MIMO array transmitter, and it will definitely give us a 10 gigabits per second. So it came back to the initial question. So we may not be able to need millimeter wave technology to achieve that. But again, another question arises, and why are we focusing on millimeter wave technology right now for 5G? Now, the reason for that is because the American, especially Donald Trump, he keeps focusing on that. He say that in the United States, they should use a millimeter wave technology. But everyone knows that if you use that, it's going to be expensive. So expensive that those mobile company or those telecom company, they can't put too many millimeter wave base station, because you need more millimeter wave base station, but each millimeter wave base station costs at least 10 times more than the 4G cell. So the cost is a problem, especially if it goes into millimeter wave technology. But still, everyone is still talking about millimeter wave technology, because we do believe that when we move to 6G, it will be another millimeter wave technology again. And so, are we going to move straight to millimeter wave at the moment? And the answer right now is not so fast. Yes, we are seeing millimeter wave AIP right now in some of the phone, especially in Samsung, and also in the latest iPhone that will be coming out next year. But still, if you look at that, they're only running at 28 gigahertz. But because of the lack in a millimeter wave base station, remember that we still lack of it. In Taiwan, we don't have any millimeter wave base station. So even if you buy this kind of phone, that is useless. It becomes a useless phone. You can only use 4G and 5G sub-6 gigahertz. And again, there are not many sub-6 gigahertz base station in Taiwan. I'm not quite sure in India at the moment. So it's useless for you right now to buy a 5G phone. So if you're a student, I would advise you not to buy a 5G phone at the moment. It's very important. It's expensive. It could be up to about $2,000 per piece. So don't buy it at the moment. You just have to wait for another 3 to 5 years and see. So not so fast. And there are 3 reasons for that. One is the atmospheric absorption. As you know that if the frequency goes up to about 10 gigahertz, then the absorption in the air, in the atmosphere, will be very large. And scattering, another problem is a scattering problem. All right. So millimeter wave propagation will be affected by the raindrops and anything that's same size as the wavelength. So it is causing a lot of a scattering of the signal. And last but not least, right now is the non-line of sight issues. That is very important, because during one of let me tell the story right now. One of the Korean guy last year, he told me they have an experiment on 28 gigahertz, and they have built this fancy car for 5G in Korea, and they try to connect it to a building. And initially they got the connection between their 5G 28 gigahertz from the car to the building, and they're so happy that they went for a drink. And after about 5 minutes, someone report back and say that the connection has been canceled. And so they went back to the car and looked at the connection. Well, everything is fine. All the things are fine. Then they realized when they came out of the car, they looked at the building and looked at their car, and they found that the leaf, the tree, there's a tree that is actually besides the car. And when the winds blow, and the leaves were somehow pointing and blocking the radio wave between the car and the building. And the absorption from the tree itself can actually cause a large attenuation. So this, not to mention the non-line of sight issues. So when it is non-line of sight, meaning that there's no way that you can have a diffracted wave for millimeter wave. And because if you do that, then the electromagnetic wave or the energy, the amplitude they're receiving will be very, very small. So this is something that those people in propagation have to study on how they're going to avoid the non-line of sight issues. And so I'm going to skip this and comes to here. So in the future right now, we're going to see some kind of small cell technology. And in Taiwan, a couple of professors at the moment, they are working in this, using what you so-called a small cell, and they try to develop that. And also in Europe and in Japan, they're trying to develop an antenna that can be integrated to the lamppost. And why they're going to integrate that to the lamppost is because when in Taiwan, because we are a democratic country, and so if you try to put a base station close to someone else's house, and this person will not be happy, because if you read the news in UK, there's the rumor that 5G base station will cause you cancer. You will get cancer. And because of that, some people without any knowledge, they try to burn down the base station, the 5G base station in UK. And so because of these rumors that the 5G base station will cause you cancer, so lots of people, they dislike having the idea of having the base station very close to your house or your living quarter. So what we came up now is the idea that we're going to integrate this small cell, and it's such a very clever way that could integrate that with the lamppost. And so there's a name for that. It's known as the small cell. And so this small cell will also be connected to a macro cell, a bigger type of my apology, a bigger type of a base station in here. And so they between them, they'll be connected to your mobile phone. They'll be running at 5G and also at the same time the LTE band, which is 4G, and at the same time also connecting to your Wi-Fi. And so you can see right now, so in the very near future, we'll be seeing more of this micro cell for 5G sub 6 gigahertz, and also all this small cell. They'll all be connecting to your mobile phone. So I'm going to skip these pages and move to a future possible design. So lots of people came to me and said, what else can I do? I mean, for the last 5 years, about 4 to 5 years. There's so many design right now has came out, and lots of ideas has been developed. So what else can I do for 5G sub-6 gigahertz mobile phone? Now, the first thing is you can do if you're a student, you're working in for PhD or for your postgraduate. Now, what I can suggest is that you can work in a multi-band design, meaning that you have to cover all this band, especially band 78 and band 79 or band 79 between 4004. This should be 4004. So you need to develop a multi-antenna type with a huge number of bands that can almost cover the 5G new radio band. And so next is the high isolation. High isolation, meaning that the antenna elements must, first of all, must be very close to each other, and the isolation must be at least about 15 dB. But obviously at the moment right now, the highest we have gone up to about 21 dB. So meaning that you have to develop antennas, a MIMO antenna that have isolation of at least about 17. 17 dB is the requirement right now given to us by some of the companies. And lastly will be the reduced users hands effects. Now, as you have seen from the previous work right now, that people who are holding their phone, now if they're holding their phone, now you know that our hand itself can communicate the electromagnetic wave. So meaning that your hands effect is large. So at the moment right now, our lab is trying to use different type of methods, trying to reduce the user hand effects. Indeed, we came up with the design and we haven't really published the paper yet. And so next we look at some of the research topics by Huawei. Obviously at the moment right now, Donald Trump is trying to choke them, but still I was invited by them to Finland last year in September, and I met some of their top scientists in there who are developing all the microwave circuits and antenna. So I did ask them and say that why not you just give me some topics that we can work on for the industry. And so they came up with all these topics. And the first one is the mobile phone for Meta ID. And this is one of the important topics because most people will want the casing of their phone to be Meta. It looks nice. It looks nice and people want it. But you know that if you have a Meta ID for your mobile phone, it's going to block all the radiation or the EM wave. So the receiving and the transmitting of the EM wave will be mitigated, be reduced. So they have to find other ways to avoid that. And so this is one of the important research topic. And the other one, as I said before, is the high isolation. It gets up to about 17 dB and tunable antenna. Because at the moment right now, because we need a huge bandwidth, you can't just have an antenna that can cover the whole bandwidth. So they're trying to develop new techniques so that the antenna can tune. And this tunable antenna has another name known as reconfigurable antenna. So that you can reconfigure the frequency band as you wish by using pin diodes. Next is the HIS and AMC technology. HIS, full name is called a high impedance surface. And AMC is artificial magnetic conductor. And the two of them are categorized in technology known as the metamaterial. So you just have to consider them as a metamaterial. Now we have used that and it will be good for some cases, but it's not, we really can't use it for mobile phone. Most people will use that for larger phone, for larger antenna devices. But because the phone, our mobile phone itself is so small that we do not have enough spaces to place our meta surface. So, but still, Huawei came up with the idea that they hope that someone can come up with a much smaller size artificial magnetic conductor that's suitable for mobile phone application. And the other one right now is the characteristic mode. Now this characteristic has been developed by someone in Europe, and at the moment right now, I don't see many papers from India, and most of it has been done in Sweden, if I still remember, and a lot also done in China. So characteristic mode is something that you can study if you are really good in maths and you're good in computational electromagnetic, and I will encourage you to do that. But if you're using characteristic mode, there's one thing you need to remember is that it will usually very validate for frequency below 1 gigahertz. But if you go into 10 gigahertz or 28 gigahertz, it's truly difficult to apply characteristic mode into that. But still, most of the industry, they say that it is still useful to use characteristic mode because they think that it can solve some of the problems they are facing at the moment, especially all the elements are being placed into the phone, and they want to see the mode of the antenna itself. So next, the one in black color is the wearable antenna. So wearable antenna, there are a few types of wearable antenna right now that we can focusing on. One is the spectacles, and the other one is the watch, and the next obviously is the AR VR. So if you're interested in that, I can encourage you to do that, to develop antennas for AR VR and also for the smartwatch and also for the spectacles. And because we have developed some of it, we have developed one smartwatch. We have also developed the spectacles antenna. You can search that from the open literature. And next will be the phase antenna. Now remember, as I said before, right now we need all the beam switching. So you need to design the network behind it, phase network behind it, and try to switch the beam of the terminals. And MIMO throughput measurement, yes, at the moment right now, in most industry, they are trying to develop the measurement system that are suitable for their phone or for their laptop. And frankly speaking, if you need to move to millimeter wave, it's going to be very, very expensive. And last but not least right now is 5G millimeter wave AIP right now. And the leading company obviously is Qualcomm. And Qualcomm 2 years ago, they have developed their own AIP known as QTM052. And now they have developed QTM525. And because of the time limit, I'm not going to go elaborate on that. But at the moment, Qualcomm is leading us a lot. And in Taiwan at the moment, yesterday I just gave a talk in AIP. A lot of people has joined the conference, and they are also focusing on the AIP antenna solution itself. So if you're interested, I would say that you should focusing on this. But again, the trouble with this is that you need to spend a lot of money, because just building one set of 1x4 AIP could cost you about, let me think, about $5,000 US. About that, 5,000. And if your simulation is not correct, then 5,000 US is gone. So I'm not quite sure how many 5,000 US I have. So I told my student that you only have 3 chances. You have 3 chances. If you miss these 3 chances, and you're not going to graduate. And so if you're going to work in this, it's going to cost a lot of money. And so money is the first problem that you have to resolve before you walk into the 5G millimeter wave antenna solution. And so here's some of the popular research topic that I was given by most of the antenna industry. And first of all, it's compact size. The antenna must be very compact in size, must be multi-band, must be broadband, and the best we must give a dual polarization, meaning that one in vertical, the other one is horizontal. And if you can develop a metal frame type or metal ID with better and high, so almost the same as what Huawei has given me. So what about millimeter wave band? I'm going to talk a little bit about millimeter wave. I think I still got a bit of time at the moment. So what can we do right now for millimeter wave? As I said before, right now it's going to be very expensive, but still you can use simulation to do that. This is one of the pictures you can see here right now. and there's a hand blockage, a finger blockage in here. You can see that there's a hand blockage in here. So, so at the moment right now, if you look at some of the papers, most of them are developed by the Korean. And because the Korean scholars are mostly sponsored by Samsung. So Samsung has spent a lot of money in the university trying to develop new antennas for their phone. And that's why if you look at the latest phone S20, they have put 5G millimeter wave antenna into that. So here are some of the research work that has been done by the Korean, and you can see that they're using the LTCC technology for this, and also they have developed the antenna at the bottom section of the phone so that it can have a very good beam steering design. So what can we do next? Now, the first thing you can do right now, you can have a mobile phone that can have a vertical and horizontal polarization, and you can also have built antennas that at the upper side down here. This is a paper from in Taiwan presented by one of the top engineer in Huawei in March 2018, and this is their simulation that they have done. And also this is some of the antenna they have designed. And they said that the millimeter of antenna will be the side edge of the mobile phone. And so I'm going to skip this. What about future what we can do right now? Now, first of all, if you're going to work into smartphone, you have to realize the fact that at the moment we have been ventured into a high body to screen ratio, meaning that you have a really large screen, and it must be up to 91.7%, which means more than 90%. So if you're showing me some kind of antenna, some kind of phone with this, meaning that the antenna that you can put in this black region will be as small as about 2 to 3 millimeter. So the challenges right now for antenna engineer is that you can only use this region, the black color here. You can only use this region, no more than 2 to 3 millimeter. And you stick all your 4G and 5G and your GPS, your Wi-Fi all into that region. And here is one of the design that was done by me and also by Shanghai University and a company called Speed. So we have developed this millimeter wave antenna, and I'm not elaborate on that. If you got time, you can download this paper. It's in the top section in here, and this is one of the picture that was taken by the IEEE Spectrum back in January 2018, because we published this paper about 2 years ago in January, and then our first author, Dr. Yu, has been interviewed by IEEE Spectrum. And you can see that we are actually the very first paper that we actually puts the integrate the 5G millimeter wave into the metal casing of an actual mobile phone. So as you can see right here, right now, this work is totally unique because this is what exactly the industrial is working towards at the moment. And you can also read this report in here from the IEEE Spectrum. So here's some of the pictures that we have shown in the paper. And the most important of all right now is that you can see, you don't see the antennas in here. The reason is that we have dig some of the cavity slot in here. And because it's a slot, then we have to use some kind of silicon gel and try to fill it up. So you're not going to see it. You can only see the white color stuff in here. So you have to add antenna in here, another antenna in here. I'm going to show you the slot. I think in the next few pages. These are some of the results that we have. But at the time right now, we can only simulate the beam steering. So it's between about 0 to 45 degrees. And so here are some of the recent published work by us. Together with some of my co-authors in China. This is one of the 8x8 MIMO work that's been done last year in October. I'm going to skip this, and this is done in this January, published in January. And we have used a very simple monopod antenna that we can have a really wide bandwidth. You can see from here, from the 3300 all the way cover up to about 6 gigahertz. And the novelty of this work is because that we can have a return loss at S11 of 10 dB. And if you read all the other work, they can only have a 6 dB bandwidth, but in this case, we have a 10 dB bandwidth. And I'm going to further discuss into here, and this is one of the very recent work that we have published in the IEEE AWPL in July, about 2 months ago. It's been published. If you're interested, you can read that. And this is a joint research with Professor Chen in Taiwan. And we have used this kind of technology. This is a metal frame. The green color is a metal frame. By using this L-shaped type with tuning stop, they'll be able to excite 2 modes in the slot, as you can see from here. Now, the novelty of this work is that we have a single slot that we can excite 2 modes. And because of that, we can have 2 modes in here, and we can cover a huge bandwidth, the same as what we have done. So this is also one of the recent published work in January. You can see that we didn't fill it up with the silicon gel, so you can see the antenna in here. So we'll dig a hole in there and try to put the feeding pin in here. And on the back side of this metal cover is this, and this is our Butler matrix. And if you're interested, you can read this paper from Microwave Journal in this year January version. So the top so the left and right side down here will be my 4G Wi-Fi and the GPS antenna. And so this is our Butler matrix that we have designed. So our latest, now I'm going to show you our latest work right now. Please give me another few minutes. Our latest work, this is published, I think this month in September 2020, and an IEEE transaction. I'm the corresponding author of this paper. It's a joint venture with Shenzhen University in China. This is a really wideband CP ME dipole antenna for 5G. And this is quite a rare type of design because we have used an SI-TABU. We've used SI-TABU feeding network, and it's used to connect to a lightning-shaped ME dipole antenna. And we also use a technology called the SCT-based power divider network. And together we try to use the sequential rotation technique, and then we can improve the aspect ratio bandwidth. And so if you can see that our 3 dB gain bandwidth is almost 25%, it's 25% between 23 to 30 gigahertz. And so this is the actual work of our design. And this also costs about a few thousand US dollars per piece. So this is the lightning shape, and this is the network, the feeding network, using SI-TABU technology. And this is the results of it. This is the S11, and the top down here is the 3 dB aspect ratio. And you can see that the beam, I can show you partial of it, but this is the beam at 28 gigahertz. So it's a narrow beam type. And the radiation efficiency is quite good, approximately about 70 to 80%. And we have a really nice gain in here, and that is almost up to about 19 dBIC. And so what about future works right now? This is some of the works that we have done and still has not been published yet. We have also developed some works and that's for 5G in the radio band between N77 and 78. And this is a very low profile type. Because previously when we look at some of the design done by other professors, the antenna development they have done is quite thick. But as you know that, as I said before, right now, the thickness of this cannot be more than 8. Cannot be more than 8. So we have developed another antenna, which the height of it is only about 5. So we have developed that. This is the simulation results, and we also have the measured result. But unfortunately, I'm not going to show it to you. Is my time up? I think I still have about.
No, sir. No, sir. You can continue.
Okay, then give me about another 3 minutes to go.
Yeah, yes, sir, please.
This is another work that we have done recently. We have wrote up the paper, hasn't really submit that yet. This is another paper that, so you can see that we're also using a really thin profile. Now the previous work that we have done, not submitted yet, but it's 5. The height of the antenna is 5. And now we reduced that to 4.6. But obviously the price to pay is that we have a much longer antenna, which is 15.7. And this is 21. And so by reducing this, we can have a much better space for the industry to put their batteries and whatsoever. And so next right now, as I said before right now, if you want to venture into new technology, yes, you have to work into AIP. But again, as I said before, you need to spend a lot of money. The first thing you need to consider is the money. Now, remember, almost 5,000 US dollar a piece. So this is something that you need to consider. And another thing that if you want to work on, as I said before, you can work on characteristic mode. And this is how you can work on. Now, this you can, if you look at the blue color casing in here. Now, this is a real life simulated casing for a mobile phone. And the one you can see on the right side down here right now, if you need to consider an antenna, you have to consider everything. Meaning that the battery, the module, the frame, the array placeholder, the PCB component, the shielding, and the glass screen. You have to consider everything. And the next thing you have to do right now, you have to buy a really expensive server. And at the moment right now, we are going to purchase the CST. So only the using CST time domain that we can really run that. And so if you need to consider everything, then the computational time will be very high. And if you apply the characteristic into here, as you can see down here, the placing of the antenna is really, really important. Now you can see, if I try to excite somewhere around here, you can see that there's a large current distribution in here, meaning that because of the current distribution in here, you cannot place your antenna in this location. So if you can place the antenna, try to adjust them in such a way, it should be showing you this. A very light green color, meaning the current distribution in the cover of your phone will be very less, meaning that you can place your antenna everywhere. So the coupling of EM coupling in here is very important at the moment, because you have to consider almost every component in the phone. So this is one of the breakdown for the Samsung Galaxy Note. I'm not going to go into that. So last but not least, right now, I'm going to show you this. This is our recent work that we have submitted to IEEE. So we have developed this in Shenzhen University, and it's a 1x4 and a 1x8 millimeter wave working between 26 to 29 gigahertz. What you can see down here, this is a 4-element antenna array, and we can see that we have a really nice beam steering in here. So previously, as I said before, we cannot measure it. But about 3 years ago, a company called the TMY Tech, they came up with this technology, came up with this box known as the beam box. So what we can do right now, we just have to place the 4 antennas with the cable and connect to this beam box. And it can be connected out from the chamber or within the chamber. And we just have to try to control it using the USB port. Control that, and we can control the phase giving to input into our antenna. So at the moment right now, this beam box has been selling like hotcakes. And I have to emphasize that it is built in Taiwan by a student of mine, actually, graduated about 16 years ago. And now he's a millionaire at the moment. And so I'm going to, yes, and I think I have to jump through this and I'll see if there's any question from the audience. Thank you very much.
Yeah, I would request if any questions are there from participant side, because in chat box there are no questions, only compliments are there to you, sir. Seems sir, only lots of compliments are there about your presentation, about your lecture.
Thank you.
Yeah, if any questions are there, please. Yeah,
hello?
one question is there. 2 millimeter wave can, I think Dr. Jitendra Sarkar, you please
yes.
Unmute yourself and please ask. Yeah.
Yes, the answer is you can do that, but as I said before, right now it is going to be very expensive. So you must have support from the government. You must have support from the government. I do believe that the military in India is doing that, because we have been in contact with the military in Taiwan, and they have spent a lot of money on that. So I do believe the military in India must be doing that in this current situation. And if you're not going to a millimeter wave, you're not going to advance into 6G. Now, remember, for 6G, we have already focused that as the low orbit satellite. You're using a low orbit, and the frequency band will be almost the same as what we have, and even further up to 66 gigahertz. So meaning that if you're studying, you have to study millimeter wave right now, or else you cannot go into 6G. Remember, the 3GPP release 18 will be talking about 6G, and that will be around about 2025, in 5 years' time. It may seem very far away, but in 5 years' time, if you do not do that, if India do not do that, then you will be very far away from the industry. And this will be very sad for all the university, because if you don't do that right now, and in 5 years' time, you can't catch up with them. But obviously, as I said before, right now, it is going to be very, very expensive. So indeed, it needs the power of the government to do that.
Before going to further questions, our director sir had joined. Let me say good afternoon, sir.
Good afternoon, ma'am. Good afternoon.
Yeah, sir. Thank you, sir, for joining. Yeah, sir, we'll take just few 2-3 questions are there. We'll take that and then we'll continue.
Okay, okay.
Sir, next question is, sir, next question is, what are the various isolation enhancement techniques for 5G antennas?
Yes, I do have a presentation on that. It's going to be very lengthy. There are at the moment right now about 6 to 7 kind of isolation enhancement technique. And I did mention one of them is using the neutralization line. But if you're using neutralization line, you need to be very careful, because if you use it wrongly, then the mitigation will be very high. So this is one of them, one of the isolation enhancement. And there are also other techniques such as reducing the ground current. Now we have a paper on that, reducing the ground current. And we also have a paper in IEEE transaction using what you so-called a self-isolation antenna. And this is a very new antenna, because you can track the antenna, the current distribution in the ground. We can try to trap it. So by trapping the current within the location of the antenna, it will not flow to the other antenna. So indeed, right now at the moment, there are about several technologies that you can use, but the most basic type right now is the neutralization line. But obviously now we have developed a few types, which is quite good. And I do believe that in India, a few scholars has done that. And I've seen some books from in the IIT, Kanpur. They have developed some of the new isolation techniques. And you can invite them for speech.
Yeah, thank you, sir. Before moving ahead, Dr. Anil Kumar, SPA, SPIU, UP has also joined this session. I welcome you, sir. Good afternoon, sir. Anil Kumar, sir. Good afternoon, sir. Yes, sir. We'll move to the next question. What are the substrate materials you suggest for mobile antennas for 5G?
What kind of substrate? Now substrate. Now, remember right now, if you're using millimeter wave, you have to use the Rogers. Yes, you have to use Rogers. But obviously, the problem with Rogers is that it's expensive. A few more times expensive than FR4. If you're using sub-6, you can use FR4. There wouldn't be any problem for any antenna below the 6 gigahertz band. But if you're moving towards 828 and 39 now, you have to use the Rogers substrate. And at the moment right now for the sub 6 gigahertz, there has been a saying that using flexible substrate. Now, flexible substrate is another option. Yes, it is. And we are using, right now there is a new type of material known as the modified PI. And another kind of substrate is known as the LCP substrate. I forgot the full name of that. But at the moment right now for Apple phone, they are using the LCP substrate for transmission line, but they are still using the PI for the antenna. So yes, Rogers for millimeter wave, and normal substrate for sub 6 gigahertz. And that's my answer to that.
Yeah, thank you, sir. Yeah, moving ahead to next question. is it possible to have a mobile device which can work in sub-6 gigahertz and 28 gigahertz and higher frequencies?
Yes, yes. At the moment right now, if you have seen if you've seen this, this is one of the work by Samsung Galaxy Note. They have put three QTM millimeter AIP in here. So at the moment right now, the Korean has joined with Qualcomm. So this 4G antenna sub-6 will be done by them. But then the 28 gigahertz with millimeter wave will be done by Americans, which is meaning that Qualcomm. So Qualcomm will sell them all the AIP module. So you can see from here, you put 3 of them, 2 of them by side and 1 of them in here. So imagine if there are 1 million phones selling from the Samsung Galaxy, you have to buy 3 AIP from Qualcomm. So you can see the opportunity in here of earning so much money by Qualcomm. So yes, it is definitely possible. It has been done right now to put sub-6 and 28 gigahertz. As I said earlier on, the Qualcomm has already developed. I'm not quite sure which pages. Qualcomm has already developed. No, sorry I forgot which page is that. Qualcomm has already developed their latest design in Snapdragon. If you read, I think it's Snapdragon X60. Now you can go to the internet and search for Snapdragon X60. The X60 Snapdragon will be released next year, early next year, 2021. And if you look at that, it will be putting the sub-6 together with millimeter wave. So yes, it has been done right now. It has been done.
Yeah, thank you, sir.
Yes, I think this page.
Yeah, I don't think so. There are more questions. Lots of compliments are there to your session, to your presentation, and nice delivery.
Yes.
So, shall we, Director sir, shall we start with the session, valedictory session? Anil sir, Dr. Anil Kumar sir had joined. Mahavir sir, Dr. Anil Kumar sir had joined. I could see the name, but he is not responding.
Yes, madam.
Yeah, sir. Good afternoon, sir.
Good afternoon, madam. Good afternoon.
So, sir, we'll start with this.
Yes.
Yeah. Dr. Sim, can we put this presentation off?
Yes, sure.
Yeah. Please be here for another few minutes.
Yes, sure.
I will make you free. I know that you have some other assignments.
Yes, thank you.
So thank you very much, sir. Never stop learning, for when we stop learning, we stop growing. Thank you, Dr. Desmond Sim, for your insightful presentation on FDP topic. You are truly a motivational benchmark to the youth of the world. Thank you very much for your excellent elaborative delivery on recent developments in 5G sub-6 GHz antenna designs for smartphone applications. You have given the future prospects also, the topics to budding researchers also. Thank you very much, sir.
Thank you.
Now we are moving towards the valedictory of this, and I know that Dr. Desmond has to go early. So, sir, you bear with us for another 5 minutes. Good afternoon to all dignitaries, guests, and delegates. With great joy and immense exultation, I, Shahnaz Ayub, FDP coordinator and hosting the valedictory session today, on behalf of Department of Electronics and Communication Engineering, BIET Jhansi, and on my own behalf, I welcome you all to the valedictory session of FDP on electromagnetics to 5G, jointly organized Bundelkhand Institute of Engineering and Technology, Jhansi, SPIU UP, ISTE, and Numergion. I welcome our Honorable Director, Professor V.K. Tyagi, sir, and request, sir, to take this digital platform and welcome the dignitaries. Over to you, sir. Yeah, sir, unmute yourself, sir. Unmute yourself, sir. Director, sir, unmute yourself.
Hello,
yes,
I am on now?
Yes, sir. Yes, sir. Yes, sir, you are audible, sir.
Hello?
Yes, sir, you are audible, sir. Sir, you are audible. Sir, you are audible, sir. Director, sir, you are audible.
Hello?
Yes, sir. Hello. Hello, sir, you are audible.
Hello?
Sir, we can listen to you, sir. You are audible. Sir, you are audible, sir. You are audible, sir. Please continue.
Hello?
Yes, sir.
Hello?
Yes, sir.
Maybe sir is audible, but he could not able to hear. That is also possible.
Hello?
Yes, sir. You are audible, sir. Please.
Sir, you are audible. The participant can hear you.
Yes, I can hear sir's voice.
Hello?
Yes, sir. I can hear you, sir. We can hear you, sir. DK, sir, can you call, sir, and inform him that we can hear him? Director, sir, we can hear you, sir. Please.
Hello? Madam?
Yes, sir. You are audible, sir. Sir, you continue, sir, please. You are audible.
Hello?
त्यागी साहब सुन पा रहे हैं?
I think he's.
सर आप ऑडिबल है सर, हम सुन पा रहे हैं
मैडम
क्लियर।
मैडम
अच्छा अच्छा
मैडम
ओके
जी जा रहा है सर मोबाइल।
हाँ बात हो गई मेरी, बात मेरी हो गई, सर बोल रहे हैं अभी। हाँ
ओके ओके
यस सर, प्लीज कंटिन्यू सर। डायरेक्टर सर। Sir, you are not audible, sir. Director, sir, you are not audible now.
Perhaps.
Sir, you are not audible, sir. Hello. Hello. हेलो सर, सम कनेक्टिविटी इशू एट योर एंड सर। आपकी आवाज भी नहीं आ रही और आपका भी वीडियो भी स्टॉप हो गया।
सर अनम्यूट कर लीजिए आप। म्यूट
हाँ हाँ आप दोबारा ज्वाइन कर लीजिए। ठीक है, ओके। हाँ सर, इज ज्वाइनिंग विद इन फ्यू सेकेंड्स, ही गॉट डिस्कनेक्टेड।
Hello, am I audible now?
Yes, sir.
Okay, thank you. Thank you. So, really, I am feeling elevated to be a part of this valedictory function, which has been organized in association with BIET Jhansi, SPIU, ISTE, and Numergen Technology. Really, I am thankful to especially Dr. Anil Kumar ji, who had always been very kind enough and had been associated with each and every activity in this pandemic. And with the support of Dr. Sahnaz Ayub, the coordinator, they have developed a good chemistry also, that whenever Dr. Sahnaz Ayub approaches him, he is unable to say no, and extending full support for organizing these activities. I'm really welcome Dr. Mahadevan, who is a great scientist of Indian Space Research Organization, who has given his valuable time and had been part of this valedictory function. I'm really welcome Dr. Raghavan also from NIT Trichy, who had been a constant support for motivating the participants for learning the new dimensions of the topic electromagnetics to 5G. Recently, just before few minutes, I joined the session when Dr. Desmond Sim was addressing the gathering, and I found him really very outstanding. I do not belong to the electronics field, but the delivery, the presentation, the content he was giving to the participant was really superb. I'm thankful to the coordinator TechUp, Professor Nigam, for extending his support, head of the department for organizing continuously activities from the department and motivating their faculty members to organize these activities. And last but not least, I'm really thankful to Dr. Sainaj Ayub, who had done a tremendous work during this pandemic and organized number of the activities from this platform, virtual platform, in this pandemic. Apart from this, really, I could not join the different sessions where technical sessions were going on during last 5 days, but I'm confident because the experts chosen were top-notch from across the country. So they might have delivered a definitely good knowledge to the participants, and definitely the participants will be benefited from their long experience of more than 30 to 40 years or so. And again, finally, I am really thankful to the organizers for successfully conducting this FDP for 5 days on such an important topic of the communication, which has really become a need of the hour, because ultimately we have to see the accuracy and speed as well. So we go from 2G, 3G, 4G, 5G, now we are talking about the 6G and all that. So with these words, I am confident that the legacy of this FDP will go a long way in the wireless communication advancements in the near future. And I wish that in near future also that BIT in association with the SPIU and other organizations will conduct such activities for the benefit of the researchers, academicians, students as well. Thank you very much.
Thank you, sir, for your motivation, guidance, and support to organize this FGP and other programs also, and sparing your valuable time with us today and always. You have motivated us. Your presence always boosts our morale. Thank you very much, sir.
Thank you, madam.
Yeah, thank you, sir. With equal pleasure, I consider it our honor to have Professor Desmond Sim, Feng Xia University, Taichung, Taiwan, with us today. Just he has delivered the lecture. I request him to share his valuable words with us. Yeah, Dr. Desmond Sim.
Yes, I have to unmute that. Yeah. Yes, I know that.
Yeah, please.
Thank you. Thank you for inviting me over in such a short notice. And I have to apologize that I have to pick up my wife afterwards. Anyway, I do believe that India can invest into 5G technology. As I've said in the comments, I say that India has to do that. Even though at the moment right now it may be delayed for a while, but the university must invest heavily on that, especially in the measurement equipment. If not, then I do believe that if we do not do it right now, then in the very near future, 5 to 6 years, when 6G came out, then we will lose the tech war on 6G. And we do believe that 6G will be the final technology for the wireless communication. So at the moment right now, yes, India has to go forward into 5G millimeter wave. But then, as I said again and again, it's going to be a very expensive investment. And this has been troubling us for a long time. And that's the reason why I have to join venture with with industry and also with my partners in China. So it will be good to join your research work with another institute, as I said, as I have already joined my research work with some other universities such as Mizoram and also other universities, also IIT. So you need to join your research work with other people. And I do really hope to see more papers from India that are in millimeter wave. And so I do hope that the COVID-19 situation in India will be contained very soon. Thank you.
Thank you very much, sir, by adjusting with Indian time and making it possible for us to listen to your insightful speech in this FDP. Thank you, sir. Hope to be connected with you in future also. Thank you very much for being part of this FDP and adding values to it, sir. Thank you, sir. Yeah, we say this FDP has been strengthening the grit and determination of the faculty members to reach academic excellence. Previously, it was planned at state level. Then slowly, within few hours, we received participation from all over country. And then it did not take time to reach to the international level. So now today this FDP is of the international level event. We had international speaker as well as international participants from different countries. Let me brief the 5 days program. First day FDP was inaugurated by Honorable President IST Professor Pratap Singh Kaka Sahib Desai. He has also shared the valuable events of IST for faculty members and students for their benefits. Then keynote address was delivered by Professor Aditya Trivedi from Triple ITM Gwalior on spatial modulation. Second day, we had lecture in an expert talk by Dr. Sachin Umbarkar from Eaton Research Center, Pune on recent trends and technologies in electromagnetics. Then afternoon session was conducted by Dr. Arjun Kumar from Bennett University on microstrip filter design. Third day, Professor Raghavan S. Continued the start of the day with microwave integrated circuit components design essentials. Then in afternoon, we had 2 sessions on our special request. Professor V. Mahadevan, scientist from ISRO, had accepted our invitation and he had delivered the talk on practical satellite antenna. Then it was followed by Dr. Hemant Juneja on planar antennas and array trends. On 4th day, we had lecture from Dr. Santosh Kumar Mehto from IIT Ranchi on soft computing applications in electromagnetics. Afternoon session was taken by Dr. Datta Prasad Torse from KLS Gokte Institute of Technology, Belagavi, Karnataka on machine learning applications in electromagnetics. We are today at 5th day of this FDP, 5 days FDP. Morning session was taken by Engineer Swapnil Gaul, founder and CEO Numergion, with Vinay Narayane from IIT Mumbai. So Swapnil Gaul, founder CEO Numergion, is also one of the organizers with us. He had taken the lecture on his very own development, interactive learning in electromagnetics, which is the India's first software tool developed by young engineer Swapnil Gaul. Then afternoon session was taken by Professor Desmond Sim, Feng Shui University. Recently, we have heard him. He has taken the lecture on recent developments in 5G sub-6 GHz antenna designs for smartphone applications. And now we are towards Numergion. The key achievement of this FDP is that though we had all interesting sessions with all eminent speakers, we are introduced to first Indian software tool with vision of making engineering education more hands-on based. Yes, from Numergion, Delhi. Numergion Delhi, NCR-based education technology startup working in the field of engineering simulations. According to the technical mentors from IIT Mumbai, this software will be India's first engineering tool that will provide the simulation-based hands-on learning, especially in engineering and technology. The startup is supported by Department of Science and Technology under EIR scheme, through which incubation support and fellowship is awarded. ISBA committee once referred to them to represent at Malaysia in one startup event where it has got 2 medals for India. We congratulate engineer Swapnil Gaul for this very innovation.
Thank you, ma'am.
Let me take the privilege to invite an eminent administrator, State Project Administrator, SPIU Uttar Pradesh, Dr. Anil Kumar, a distinguished personality, to address the August gathering. Over to you, sir.
Thank you very much, madam. Indeed, it's my great pleasure, as well as a proud moment for me, when a small beginning, your plan to make it happen at the state level for all the technical institutions of Uttar Pradesh. And you truly told that now it has converted to an international FDP. Even in physical mode of FDP, and more particularly for 4 or 5 days FDP sessions, the level of participation has been very less. But when we talk about this session, in every session the participation was always more than 90. Even in this valedictory session, we can see it is around 90. So the presence of participation, it itself indicates the hard work being done by BIET Jhansi, and more particularly the person who conceived the idea and constantly day and night working for this for the long 5-6 days. Ms. Sanaz Ayub, I especially thank you, madam, and we feel proud of you because you have shown the way for other institutions and other faculty that when you have the will, you can make it happen, and you have made it happen. So it is a proud moment for TechUp as well as the SPIU Uttar Pradesh as well, because such good programs being conducted by you, giving a clear message to the institutions, NPIU, MHRD and the World Bank that things are happening in Uttar Pradesh, more particularly during pandemic session, and giving a clear message that things is happening and things will happen. I express my heartfelt thanks to the international delegate, the expert, Dr. Chow Yen Desmond Sim. And it's very nice when he talked about antenna designs for smartphone applications, and more particularly, he made it happen to be an international event with the collaboration from Feng Xia University, Taichung, Taiwan. I express my thanks to the director of the institutions, who is not visible on the platform, but it is only because of his good leadership and his total support and freedom to the faculty that they are planning, designing and implementing the way it should happen. I also express my thanks to Professor Mahadevan, Professor V.M. Mahadevan, the former scientist from ISRO, and he is a known scientist in the country, and more particularly known as Chandrayaan scientist. I have also no words to thanks to the TechUp group of BIET Jhansi, Professor D.K. Srivastava, Head ECE, as well as Professor A.K. Nigam, TechUp 3 coordinator, because it is their support to Ms. Ayub which is converted into the successful implementation of the program. And I will also express in absentia though my heartfelt thanks to Professor Desai, Pratap K. Desai, who is the president of the Indian Society of Technical Education, who at one request heartily agreed to become one of the co-organizers and use the logo of IST and name as well for this program to happen. And he was personally ensured that he is present there during the inaugural session as the chief guest. And more particularly, the special thanks to the participants for long 5 days. It is unbelievable, but it is true that they are constantly on both the sessions. It is not that we are conducting 1 hour and 2 hour sessions. For both the sessions, forenoon and afternoon, they are continuing participating, and they are the people who have made it happen and made it successful. With these few words, I express my heartfelt thanks once again to one and to all. Thank you very much, madam.
Thank you very much, sir, for your support and guidance. Words cannot express my gratitude. Thank you, sir, for your motivating words, your constant support and guidance. It is great honor of our institute to have a very dynamic technocrat, a seasoned scholar and navigator of this flagship of knowledge and eminent personality, Professor V. Mahadevan, scientist ISRO and currently professor at Electronics and Communication Engineering Department, PES University, Bangalore. The whole digital platform is vibrating and echoing his prominence. I request you, sir, to bless us with your words. Professor V. Mahadevan, sir, I request you, sir.
Good afternoon to everybody who is present, all dignitaries and the delegates being present here in this. It was a great pleasure for me to be a part of this FDP. So initially we generally start off, but we don't continue, we don't really listen to every session. Here, the sessions were so good that every day we made it a point to make sure that we are present in time and then listen to every topic which is done, because the topics are so well selected and apt for this. First thing is, once you write 5G, you are sure to attract a lot of people. If you don't write that, and second thing is, one place there is a machine learning. See, these two words, machine learning and 5G, these are two catchy words which will attract a lot of delegates for any session. Okay, so that notwithstanding that, now after the inauguration on the first day, we had an excellent lecture by Dr. Trivedi, I suppose, on the space modulation. It was an extraordinary lecture, and that gave such a good insight into the subject. At the same time, for every student to find out what exactly he has to see onto that. So that was a very great lecture. And then we ended with an excellent lecture on 5G by a very eminent person who showed us the way as to how we really have to do it. In fact, long time back, I once heard from Professor Paul Raj from Stanford University during our 3G time. Possibly we were not going to 4G. He said that anyway, India, we have missed 4G. You have to make sure that you catch up with 5G. So it is high time that we catch up with 5G. And I'm sure with such an amount of intellectual manpower available in India, in both university as well as industry, I think we should be able to pool the required resources and make sure that we are a competitor and get at least the national level requirement for 5G. So that is our dream. I am sure in next 3 to 4 years time, we must be getting ready for this, and I'm sure we'll get our band also allotted. The government is on the line, and so we'll get our bands also allotted and start working fully on that. So that's one very great dream. So in between, we had a number of other sessions where we had design details. We had details of even in the software, on the software analysis. And some of them are with the algorithms. And each and every speaker, when he spoke with such great clarity. That is what is important, with great clarity. We didn't find anybody fumbling at any time. They each one spoke with such great clarity, and every question which was posed was very well answered by the speaker. That's a very great thing. So after every session, the organizers also were not in a hurry to just wind up. They made sure that every question which is addressed in that is posed, and the answer is obtained from him. And even in some cases, they even got the acknowledgement from the person who asked the question to say whether he is satisfied or not. So it's a very great method of conducting the FDP. So that is one thing which I saw. And then the last and not the least is the final this software which has come up. People have been using all softwares from all over abroad, and we definitely the local faculties will definitely like to use something which is developed in-house, that is within India. And we had from Swapnil this thing, a very good demonstration of what his software can do. And this is only a start. as I would say that it is just an alpha or a beta version. So now after you get the input from various universities and this, it will go very fast and you must be able to come to a full-fledged version as how they have done in others. It has been the case for all the softwares which have really come up. So it is excellent this thing attempt by a student who has studied the subject very well and has gone through that and then given that. Now added to that is that instrumentation part which has also come. So that has also added very much. I mean, all these things together has given a very good platform by the organizers. I should say that all the 4 major organizations which have taken place, they have really given them an excellent platform to choose what exactly is their area of research and go ahead with that. I think with these few words, I will stop this presentation, and I wish all the students and the faculty the very best. Thank you.
Thank you, sir. I wholeheartedly thank you for your inspiring and encouraging words. We wish to express our gratitude to you, sir, for being with us on this event today also and throughout 5 days. Your presence was motivation to all of us. Thank you for adding the values to this FDP with your presence and intellectual words. Thank you, sir.
Finally, I would like to thank each and everyone who has made this possible, specifically the organizers. And the organizers were not in hurry at any time. That is one very great thing which I saw. Okay,
yes,
so I really thank everybody.
Thank you, sir. It gives me immense pleasure to invite the very popular, the voice of the microwave community. I feel so energized to invite such a legend of microwave engineering, Professor S. Raghavan, sir, to bless us with his address. Over to you, sir.
Valuable 100 participants who have expressed excellent feedback in the chat box. So this is a certificate to the director and also Dr. Anil Kumar and also the TechCube 3 that the 5 days FDP went with a grand success. Then in these 5 days, I went through the biodata of 2 persons. One is the director whose biodata runs to 21 pages, not the papers, it is his ability. The second one is the organizer. I have forgotten her name. I keep calling biomedical Madam Jhansi Rani. Now, I have got a small request, having gone through 5 days and seen. Now, BIT has been known throughout from India to Kashmir, plus outside the world, outside India also. I have got a sincere request to the director and also Dr. Anil Kumar and also the TechCube 3. And one of there are 3 messages the director has given to the BIT community. After that, one is social responsibility. And also IEEE has got one epic engineering project for community service. Then, you know very well, in 2 months, technology oriented COVID also is there. So now seeing all those things and also the enormous support by the wonderful participants, plus the excellent resource persons, they did not talk a theory, they talk only the practical, which will work everywhere. So with all this, I want to put forth one small request. I do not know how far the role model director and Dr. Anil Kumar will take it up. Maybe I will be happy if I get some indication about my request. The request is the successful coordinator. I found that she got qualified in biomedical engineering. Not only that, she has worked a lot. 2 persons have completed broadband techniques of microstrip antenna. So she has done a lot. And Dr. Swapnil's one of the guides is Dr. Girish Kumar, one of the persons in the world who can talk about the biological effect of microwaves. And the microwaves and biomedical can do wonders. So what I want to tell is, I do not know whether it is possible by the TechCube 3. Now that you have become this much popular, you should do some service to the society. What I coming to the point is, I wish the same set of organizers, at least by principle, should agree to hold a FDP on biomedical engineering. By mental telepathy also has got some relationship with microwaves, and it plays a very big role. CT, MRI, FSS, all is doing wonderful things on biomedical engineering or something related to that. In that case, some more participants will come. It is not only the participants, the service you render will go directly to the society. This is what the request I want to put forth to the Honorable Director, Dr. Anil Kumar, and also the TechCube group. And last but not the least, Make in India, the first ever software done by youngest person, Dr. Swapnil Gaul. I'm simply calling doctor because this work is more than a thesis work, practical work. And that should reach the visionary Make in India person, Honorable Prime Minister. And only when one or two things have to be added, then definitely this will come in the top, as Dr. Mahadevan is here, as Mars is in the space mission, his software also reach that much position. Maybe by evening, I would like to know whether my request is in principle at least accepted by the Honorable Director and the TechCube group. With this, I would like to, one more thing I would like to say, all the source people, they told so many practical things, from high power microwaves to energy harvesting. I have seen people talking energy harvesting. This is a young person. Again, Dr. Girish Kumar's student who designed energy harvesting. Such people Dr. Shamim has chosen. So I wish you select wonderful biomedical people of India, and if the director approves, you kindly hold that FDP also, do one more service to the society. Maybe director I cannot tell directly. Maybe I would like to tell Dr. Anil Kumar's opinion.
Sir, unmute yourself, sir. Anil Kumar, sir, unmute yourself, sir, please.
Yes. Can you hear me, madam?
Yes, sir.
It is indeed great pleasure for us, and we feel proud when luminary like Professor Raghavan from NIT Trichy, when talk about good words for the organizers, and more particularly the BIT, and more particularly you. He has truly talked about, he has forgotten your name, but he's talking about like Jhansi Rani. You have been truly instrumental making it happen prior to the day one till today. I express my heartfelt thanks for the kind words by Professor Raghavan, and we are looking forward for more connect, not necessarily in the field of FDP, in some other area and domain area, so that we can be benefited in Uttar Pradesh by his expertise in this particular field, as well as in institutional building, in governance, in various other reforms as well. Thank you very much, sir. Thank you very much.
Thank you. One more thing I want to add, in the department itself, there are signal processing person. The Atul is a signal processing expert. Our director is a chemical person. So that way, microfluidics, biomims is a combination of many engineering technology. So it is not only biomedical. So that is what I want to put little more to the Honorable Director's view.
Thank you very much, sir. Thank you.
Yeah. Hello.
Yes, sir. Yes, sir.
I would like to add, I'm really thankful to Professor Raghavan, yes, and he has given very good suggestions. And Professor Raghavan, I can assure you that time to time, I motivate the faculty of this institute to go for the interdisciplinary research. Number one. Number two, the research must be on such areas which can benefit the society directly. So, because I have visited number of the US universities, there the persons from the different domains like electrical engineering, computer science, chemical engineering, biomedical engineering, medical doctors, they work in a coherent team and they deliver the outcome of the research to the society for number of the diseases like cancer and heart issues, number of kidney problems. So they are being addressed in association by collaborating different scientists or the experts in the area. I had always motivated my faculty in this institute, and I will make it a point that in future we will. Today itself, I had a meeting with the head of department and the professors, and I have conveyed them this very categorically that I will render full support if you work in collaboration with different streams. So I assure you, sir, we will do something in this direction, and your suggestions are well appreciated. Thank you very much, sir. Thank you very much.
Extremely happy, sir. I never thought such a high-ranking person will come out immediately. That shows your broad-mindedness, and definitely, whether you conduct FDP or not, your words are sufficient. Thanks a lot, sir.
Thank you, sir. Thank you very much, sir.
Thank you, Dr. Anil Kumar. Thank you, Honorable Director, sir. And thank you, Professor Raghavan, sir. I need to multiply thank you word infinite times to match it with your efforts, sir. Thank you for being with us today and for being us with throughout the FDP with active involvement and guidance. I wholeheartedly thank you for your inspiring, encouraging, thought-provoking address, sir. Thank you very much, sir. Yeah, may I ask a participant, anybody from participant to provide his or her feedback? May I ask any participant? Is it
And your
possible?
coordinator is not there? Coordinator, head of department?
Yeah, he's there, sir. Professor DK, sir, is there.
What about coordinator?
Coordinator, myself, I am here, sir.
Coordinator, take you by me.
Take you coordinator, sir.
Sir, I am also available, sir.
Okay.
Yeah, he's also available, sir. Yeah. Actually, he has
Good
put
evening,
his,
sir. I am also available.
Okay.
Good evening, sir. Director, sir. Good evening. BIET Jhansi, sir. I am available.
Sir is asking about Nigam, sir.
Okay.
Nigam sir is there or not? Sir is asking about that.
Nigam sir, I was asking to the head of department also.
Yeah, he's there, sir. Professor. Okay.
Available, sir.
Yeah,
may
I ask participants, sir? May I ask, sir, Honorable Director? May I ask participants' feedback?
Yes, sure.
Yeah. Anybody from participants?
Hello, ma'am. In the
Yeah.
participants, we are having Dr. Kapil Saraswat, who is like who has done very great work in the research domain. His expertise is also in computational electromagnetics as well as low frequency sensor designs part. So yeah, and he had done the PhD in IIT Kanpur. So so
please,
I would like to request Dr. Kapil Saraswat.
Kapil Saraswat. Okay. Yeah, please. Dr. Kapil Saraswat, please, sir.
Hi, good evening to all of you.
Yeah, good evening. Good evening, sir.
Thank you to Shahnaz ma'am for conducting this FDP, BIET Jhansi, and Swapnil to conduct this flawlessly. I would like to thank all the experts, including Dasman Sim, Professor Raghavan, and other people like Srivastav ji, Manveer ji. It's a great opportunity for the Indian people because of 3 facts or 4 facts. The first one is the convenience to the participant, because it's very easy for everyone to attend. Like from last 7 or 8 months, I'm continuously attending every webinar in RF and microwave domain. And I really love this, this way, because in a room, I'm attending all the workshops and webinar. It's a most interactive way to communicate with the people, because it's a chat box. Many of the people are hesitating to communicate with other people. So it gives an opportunity, and the national and international experts are there. And the last part is the Make in India thing. So like we recently see that 3 or 4 people are working towards, they are developing something in which India is lagging behind, but now they are. So it gave a good opportunity to look at all the aspects of those things. And all are very nice presentations, very smoothly going on. Like from last 5 days, I'm attending this thing. So it's a wonderful opportunity for me as well. So thank you very much.
Yeah, thank you, Dr. Kapil, for your valuable feedback. May I ask some more participants to can add on his or her feedback?
Good evening, all. I am Aarti from Thapar, Patiala.
Yeah, good evening, madam.
Yes, ma'am. I really thank all the organizers, especially you.
Madam, you put on your camera, please, madam.
Okay.
We would like to see you. Yeah. Yeah, please.
Yeah, hello, hello. Yeah.
Great.
Actually,
I really thank all the organizers and coordinators, especially for arranging such informative sessions. They were all very informative. This one by Professor Desmond, and so that on soft computing. All beside that, all the sessions were very good. Some were related to my field, and I was really benefited from them. And I hope that in future also we get these type of FDPs from BIT. So thank you so much, ma'am. Thank you all the dignitaries present here. Thanks a lot.
Thank you, madam, for your nice, wonderful feedback.
Thank you.
It really matters us a lot. Thank you. Thank you, madam.
Thank you. Thank you all.
Yeah. Can I ask Professor D.K. Srivastava, Head Electronics and Communication Engineering, for concluding remark? Professor D.K. Srivastava?
Yes, madam. Yes, madam.
Yeah,
Thank you.
yes,
What to say about this FDP? The FDP has achieved a very high level and has become international activity because the professor from abroad, Chow Desmond Sim from Feng Xia University, I delivered very wonderful lecture, and the feedback in chat box itself shows that how the FDP was beneficial to the participants, giving wonderful feedback. And we got the certificate from Professor Raghavan sir, who he said about it's the grand successful. So I very much thrilled and excited, very much happy that we able to have such a successful and high level with the help
Your voice is breaking, sir. Your voice is breaking, sir.
Okay,
Yeah.
okay. It's not clear?
Yeah, now it's clear.
It's okay.
Just few minutes,
So
yeah, just few minutes before.
I'm very much delighted that this FDP is very much successful, and the participants are benefited with this FDP, as it shows from the feedback in the chat box. I am thankful to Anil Kumar sir, SPIU UP, who constantly supporting us and motivating us so that we are able to organize such FDPs. And at this time, with the help of him, we are able to collect, brought in this FDP, a very high personalities like Professor Raghavan sir, Mahadevan sir, and they have, and this Desmond sir. This has made this FDP an international activity, and this is a very proud moment for us. And I am very much thankful to our Honorable Director, sir, who is constantly supporting us, motivating us. And today in afternoon, in the meeting of head of departments and professors, he himself motivated us to do interdisciplinary activities. I am very much thankful to Professor Desmond, sir, who gave wonderful lecture and made this FDP, gave this FDP an international platform. I am very much thankful to Raghavan, sir, who constantly attended this FDP and motivated us. Sir, your comments are very much valuable to us. I am very much thankful to Mahadevan, sir. Sir, your lecture was wonderful, amazing, and we are benefited with it and motivated with and were motivated with it. Lastly, I am thankful to Nigam sir also, who manage our TechCube formalities. I am thankful to Dr. Sehnaz Ayub, coordinator of this FDP, who is constantly organizing such webinars and doing very hard work to make such FDPs to very high level and very successful. I am thankful to Dr. Atul Kumar Dwivedi also, who look after the tactical issues. And I am thankful to Swapnil also, who has given wonderful sessions to benefit our participants. I am also thankful to our participants who have attended with their full interest and motivated us with their feedbacks, their wonderful feedbacks. I am thankful to all who is directly or indirectly related with this FDP. Thank you very much.
Thank you, sir. Let me thank you. Professor D.K. Srivastava, let me thank you. Dr. Anil Kumar, Professor Nigam sir is there, or sir Nigam sir is there? Nigam sir, are you there? I think he's not here. He couldn't join, I think. May I request Dr. Mahavir Singh to please propose the vote of thanks?
Thank you, ma'am.
Yeah, thank you, sir.
So, on behalf of the State Project Implementation Unit Uttar Pradesh, the Bundelkhand Institute of Engineering and Technology, Indian Society of Technical Education, and Numergon Private Limited, and my own behalf, I would like to convey my regards and thanks to our co-organizer, Dr. Pratap K. Desai, who is the President, IST, Dr. V.K. Tyagi ji, Director, BIET Jhansi, Professor A.K. Nigam ji, TechCube Coordinator, BIET, Professor D.K. Srivastava, Head, Electronics Communication, and a special thanks to Dr. Sehnaz Ayub, who is the Dean, R&D, and the FDP Coordinator from the BIET Institute. I would like to thank our distinguished guest of this valedictory session, Professor V. Mahadevan, who is the great scientist from the ISRO, Professor S. Raghavan from NIT Tirchi, Dr. Chow Yen Deshmond from Feng Chaya University, Taiwan, for accepting our invitation and agree to be part of this 5 days online faculty development program on electromagnetic to 5G and making this FDP interesting and meaningful. I would like to express my gratitude to our invited speaker, Professor Aditya Trivedi, IIITM Gwalior, Dr. Santosh Kumar Mehto, IIIT Ranchi, Dr. Hemant Juneja, NIT Tirchi, Professor S. Raghavan, NIT Tirchi, Dr. Sachin, Aton Research Center, Dr. Arjun Kumar, Bennett University, Dr. Datta Prasad, KLS Gotki University, Institute of Technology, Karnataka, and especially thanks to Mr. Swapnil Goel and Mr. Vinay, who has delivered their expert talk during this 5-day FDP. I would like to thank Dr. Anil Kumar, who is the State Project Administrator, SPIU UP, and the main driving force behind the success story of SPIU UP. I also appreciate the support of SPIU officials, Mr. V.K. Singh ji, Mr. Vinny Surana ji, and others who are involved directly or indirectly in this event to make the success. I would like to convey my thanks to Ministry of Education, the World Bank, the NPIU officials for their contribution toward the success of this FDP. At last, I thanks all the participants who are attended this online FDP from various corners of the country, because without support of them, the success of FDP was not be possible. So once again, thanks to all for joining us. Jai Hind.
Yeah, thank you. Let me thank Dr. Mahavir Singh Naroka for his tireless cooperation to this FDP. And we are now...
Madam, 1 minute, madam.
Yes, sir. Yes, sir. Please.
There was a person who has been helping all these 5 days by sitting behind the screen in IT technology, and he is no other than the DSP expert,
Dr. Atul.
Atul.
Yeah.
So Atul was silently managing all the IT work. A special thanks to him and also Dr. Mahavir Singh.
Yeah, thank you. Thank you. Yeah.
Thank you so much, sir. Thank you so much.
Yeah, thank you, Dr. Atul.
I thank Professor Raghavan for introducing me to this FDP. Right, that's because of him that I got in. And then, of course, a special mention to and kudos to the organizers and especially to Shehnaz Madam.
Thank you, sir. Thank you. Thank you. So, shall we close the event, sir? I request participants to take the feedback link from chat box. And please ease our work of certification by putting your spelling your name properly, so that
Shehnaz ma'am, thank you very much.
Yeah, thank you, sir. Thank you.
Thank you very much. Actually, I am busy in meetings. That's why I am not listening to what you're saying. But really, your speech is very nice, FDP ma'am. Thank you very much.
Thank you so much, sir. Thank you.
Thank you.
Thank you, sir. Yeah. So, I will request Honorable Director to declare this event as closed. Honorable Director, sir.
Thanks to one and all for this wonderful event, to become part of this wonderful event which has been organized for the last 5 days. Thanks to one and all, especially Dr. Shehnaz Ayub, for conducting such an excellent activity for the benefit of the persons related to the communication engineering. Thanks one again to all of you. Thank you very much.
Thank you, sir.
Thank you.
If everybody had noted this feedback link, I will request host to please end the meeting. Have you all taken the feedback link? I request host to please end the meeting.